All right, so let's continue by giving some explicit ways of calculating some discriminants. So you have a bunch of formulae which will help us do this and make this problem a lot easier. So we begin with a proposition 2.2.16, which says the following. So let K be a number field. With basis. So this doesn't have to be a basis of this doesn't have to be an integral basis, just a basis. B B1 to Bn, and let sigma 1 to sigma n be the embeddings of K into the complex number as usual, and I let M be the following matrix. So it's going to be sigma 1 of B1. Here I have sigma 1 of Bn, sigma n of B1, and then here I have sigma n of Bn. So this is the matrix I get by applying my embeddings to my basis. Then what does the result say? Then the discriminant of this basis is the determinant of this matrix squared. Great. So not properly proof. This might not look super useful, but we're going to be able to use this to construct a lot of useful formula. So start by proposition, what is it, 1.7.6, we know the following. That if you consider the trace from K to Q of Bi times Bj, you get the sum over, indices, right? Sum over K of sigma K Bi sigma K Bj, right? The sigma is a ring homomorphism, so sigma of the product of the two things is the product of the two sigmas. So, and you remember the trace is just the sum over all the embeddings. And you notice that this is the same, which is the same as the ij entry of the following matrix. You take your matrix M that I have above, transposed times M. So just think about what this matrix times transpose would look like. All of the entries look like this. So therefore, the determinant of TB, remember this was the matrix that I was associating to my basis B way back when. I can maybe scroll back and find it. Yeah, it was this basis, this matrix coming from the traces. This was definition 2.2.1. Okay. Therefore, we have is the determinant of this is the same thing as the determinant of M transpose times M, which is the same thing as the determinant of M squared. And we're done. Great. So we have two slightly different matrices which we can use to compute the discriminant with. The first one was this matrix of traces, and here's this matrix with embeddings. So that's one thing. So now let's start using some special looking types of bases for our spaces, which is how I'll make our calculations easier. So recall that by the primitive element theorem, what was this, 1.5.11, for any number field K, you can find, you can always find some alpha in K such that K is isomorphic to Q alpha, and therefore if you consider this what's called the power basis, with n being the degree of your field, this is a basis. Then therefore this is a basis for k over q. I'm not saying anything about integral bases, just a random basis. For this specific basis, something that looks like this, just powers of some element. This is called a power basis. The discriminant can be computed quite easily. In this case, we have proposition prop 2.2.17. Let k be a number field. And b one, this basis 1 alpha to the n minus 1 for some, say, alpha in k. Then what does it say? And the discriminant of b of this set of elements b is the product over I less than j of, I'll say sigma I of alpha minus sigma j of alpha all squared, where with the usual notation, these sigma i's are the embeddings of k into the complex number. Great. So notice that these aren't zeros because it's I strictly less than j, so these things don't vanish. Again, here we're going to use some nice fact about these van der Monde matrices. Maybe you've seen this from linear algebra, but if not, I'll recall. So first, recall the following classical result. Maybe we do this a lot. Recall basic results from linear algebra which you haven't seen before. In which case, here are some facts about linear algebra which we're going to assume and not prove. But these are usually things that you can prove. These are things that you can just prove using what you learned in linear algebra. So recall that what do I say? That we have the following, I'd say, identity from linear algebra, which says the following. If I look at the determinant of some matrix which looks like 1 x1 squared, say xn to the n minus xn x1 to the n minus 1, and here you have x2 to the n minus 1, and last 1 xn to the n minus 1. If you have such a may I want n minus 1 here, so it's actually a square matrix. The determinant of a matrix which looks like this, where the entry is just along the rows, just take powers of some element. This is a standard result that this is the product over I less than j of xi minus xj. So the determinant of this thing is just this expression here. Now, if you just combine this result with the previous proposition, you plug in these sigma i's, where in the previous proposition we have said that we could calculate the discriminant using this sort of matrix. We have a basis which is now just like 1 alpha squared, so the first one's going to be a 1 here, and then you're going to have alpha to the n minus 1, say. So this matrix, when you plug in your basis, just looks like some matrix like this, and now we just use this result. And this just works for any xi's. So combining this with proposition 2.2.16 gives a result. Great. And lastly, I'm going to give you probably the most useful formula for calculating the discriminants. But that's the last one I'm going to give you. But first, before I give it to you, I need to give a lemma. So before giving the next formula, we need a lemma. So what is this? This is lemma 2.2.18. So let f be a monic, irreducible polynomial over a number field k. And alpha one of its roots. Say in complex numbers, doesn't have to be a root in k. One of its roots in the complex numbers. Then if you look at the derivative of f of x and apply and evaluate at alpha, this is the same thing as the product of all roots beta different from alpha of alpha minus beta, where beta are the other roots. Oh yeah. Proof. This isn't hard, just write it all out. So write f of x. We know that it has a root alpha, so x minus alpha times g of x. And since we're working over the complex numbers, we can do this. Over the complex numbers. Now, notice that g of x is going to be the product over all the other roots. So the other roots beta different from alpha of x minus, of x minus beta. Why does the root alpha only have to appear once? Well, remember that we proved the separability lemma, saying that if you had a monic irreducible polynomial, then the roots always had just one multiplicity. You couldn't have repeated roots, essentially. So g of x has to be this sort of product. So differentiating we get f prime of x is g of x plus x minus alpha g prime of alpha, g prime of x. Now just evaluate at x equals alpha to get a result. Great. So you plug alpha in, this term vanishes, you end up with a g of alpha, which is exactly the quantity we want. So why is this useful? Well, here's a really quick way of calculating a discriminant if you have some power basis. So here's a proposition 2.2.19. If I let k be, say, q, alpha be a number field, with n being the degree, and we take b to be 1 alpha to the n minus 1, then the discriminant of this particular basis equals minus 1 to the n minus 1. Oh, so it's n times n minus 1 for 2 times the norm of some specific element. And what's this element? Well, it's what you get from taking the minimal polynomial of alpha over q, because we're working over q. You differentiate it and then you evaluate at alpha. So I just wrote where m alpha primed is the derivative of m alpha q of x. Remember, this was a minimal polynomial. Proof is actually not so hard now that we have all of this stuff. So proof by proposition 2.2.17, we have the discriminant of b is the product over I less than j of sigma I alpha minus I decided to implement some notation here, so I'm going to use alpha I minus alpha j squared, where say alpha k is, you do sigma k of alpha, where sigma k are the embeddings. Okay, so I look at the image of alpha under the nth embedding. I call that alpha n. So now, how many terms are in this product? So note that there are n times n minus 1 over 2 terms, which equals, if you think about this is 1 plus 2 plus n minus 1. If you think of how many, if you fix a j, how many choices for alpha you have, and so on. So you have this many terms in this product. So if we rewrite each term, say alpha I minus alpha j squared, as minus alpha I alpha j times alpha j minus alpha I. So I'm just rewriting them like this. I'm putting 2 minus 1s in here. We get the following. You plug it into the formula, so you get minus 1 to this number of terms that you've changed, so it's n times this. Then you have the product over I equals 1 to n, and the product of I different from j of alpha I minus alpha j. This is what this product turns into. And then now, by lemma 2.2.18 and proposition 1.7.6, we see that this norm this is product from I equals 1 to n of m primed alpha I, because the norm is the product over all the different embeddings, and then the embedding somehow will commute with being inside of the minimal polynomial or not. So yeah, this is the same thing as product of I equals 1 to n of sigma I of m alpha primed of alpha. This commutes because sigma I is a ring homomorphism. Anyway, this thing, which we can then just rewrite as the product from I equals 1 using the previous lemma, and this is the product from I different from j of alpha I minus alpha j, which is exactly the expression we had up here. So here's my expression for the discriminant, and here's what this norm of this thing looks like, and you can tell that they from these two things you get the result. Right, just this term is this term here, so if you plug in this into here, you get discriminant of b is this sign times this thing, and that's exactly what this proposition was doing. So let me give you an example of why this is good. So example 2.2.20, let's let alpha be a root of x to the 8 minus 2, which is irreducible by Eisenstein with p equals 2, right? Then q of alpha over q, this degree is 8. This is a degree 8 extension and has a basis of the form 1 alpha to the 7. So if I use the above proposition, therefore, the discriminant of this basis is minus 1 to the degree, so it's 8 times 7 over 2 times the norm from k to q. I'm guessing I should do q alpha. The norm from q alpha to q of m, we call this m alpha primed evaluated at alpha. What's this? Well, this is, the sign is even, so the sign disappears. This is the norm from q alpha over q of what element? Well, if I differentiate this polynomial and evaluate at alpha, what do you get? You get 8 times alpha to the 7, which the norm is multiplicative, so now I can split this up. This is norm from this thing of number 8 times the norm from q alpha over q of alpha to the 7, which you can work out. This is 8 to the 8. If you have an integer and you take the norm in a field of degree, say 8, then you're just going to get that same integer to the power 8. So if this was 9, then you get 9 to the 8. So it's not, yeah. You get 8 to the 8 times something else, times the norm of alpha to the 7. And the norm, you figure out, you just got to figure out what the norm of alpha is. The norm of alpha is minus 2. So this is minus 2 to the 7, which equals minus 2 to the 31. Here we say, here we use that the norm of alpha to the 7. This is the norm of alpha to the 7, and that the norm, keep on the right k, of alpha equals minus 2. Cool. So here's that was an easy example to do, and all you need to do is be able to compute norms of elements. Now that we have these formulas for discriminants, here's a let me give you some lemmas which are going to help us in computing an integral basis, which is all about computing some sort of discriminants. So here's a useful lemma, 2.2.21. Let k be q alpha, and alpha an algebraic integer, such that its minimal polynomial satisfies Eisenstein's criterion. So yeah, P. Then none of the elements phi of the form 1 over P times x0 plus x1 alpha plus xn minus 1 alpha to the n minus 1. None of the elements that look like this are algebraic integers. Where here n equals the degree of my field, and the the xi's are between 0 and p minus 1. P minus 1. This might look like a strange number, but from the previous lecture, I'll just scroll back. We talked about this lemma, which was giving us an algorithm for computing integral bases. It was this lemma 2.2.7. And it said that if you didn't have an integral basis, well, then an element of a certain form had to exist. What we're saying now is that if you have a field constructed by a polynomial which is Eisenstein at P, then these elements can't exist in your field. So what's this going to be useful for? Well, we're going to be trying to find an integral basis. You might have some prime squared dividing the discriminant, so you might have to worry about trying to use this algorithm, this lemma, applied to this situation. But then, if you know that your thing is Eisenstein at P, then there can't be any elements of this form. So the element, the basis that you start somehow has to be Eisenstein. It has to be minimal. Doesn't quite have to be an integral basis, but at least this prime P, whose square is dividing the discriminant, isn't one that you have to worry about. Maybe it's confusing, but we'll do some examples later. But the fact that these elements can't be algebraic integers will be very useful for computing integral bases. Okay, so here's the proof. So suppose for contradiction that we have some phi in OK, and let xd be the first non-zero coefficient. So let's assume that this element here was an algebraic integer, and let's take the first x, which is non-zero. So we have phi equals 1 over p. All of the previous coefficients are 0, so it just looks like this. xn minus 1 alpha to the n minus 1. So this is what the thing looks like. And again, these xi's are still between 0 and p minus 1. So we have this element, and we're assuming that this is an element of OK. Now rewrite this as the following. Fine, I'll write just 1 over p xd alpha to the d plus alpha d plus 1 times some beta for some beta in OK. I'm just going to group up all the other elements and write it like this. So next we multiply through by what is it? It's alpha to the n minus 1 minus d. So I'm going to multiply this whole expression by this. Then we have, so I'm just taking this element and rewriting it in certain ways and then manipulating it we're going to achieve a contradiction. So if I multiply this expression by this, multiply this expression by this, we get the following: x d alpha to the n minus 1 plus alpha to the n beta, and this is divided by p, this is divided by p, and we're saying that this is an element of OK. Now, since m alpha satisfies Eisenstein's criterion, at p, we see that alpha to the n has to be p times f of x for some, say, f in some polynomial. So you take some polynomial and evaluate alpha, because you think of what I'm just taking the minimal polynomial. If you plug in alpha and then somehow rewrite, the fact that it's Eisenstein means that you can rewrite it like this. Therefore, the above, if you combine, this looks like this, so we can plug in alpha to the n into this thing, so we get x to the d alpha to the n minus 1 over p plus beta f of alpha. All of this is a algebraic integer, but then we know that beta is an algebraic integer, and this can still be an algebraic integer because this is a linear combination of algebraic integers. F of x is some polynomial in z of x, So this means that xd alpha to the n minus 1 over p is a algebraic integer. So if I have the sum of two things and one of them is an algebraic integer, I can subtract it, and now this has to be an algebraic integer. And let's now just compute the norm of this. Now let's compute its norm. So norm k to q of xd alpha to the n minus 1 over p. These d's should be subscripts. I should make them small. What is this? No, xd is just some integer coefficient. So you're just going to get xd to the degree of your field coming up at the front. The norm from k to q of alpha to the n minus 1 using the multiplicativity of the norm. And at the bottom you're going to have a p to the n because the p somehow comes out as well. Now we're going to start using the Eisenstein criterion again. So by Eisenstein, well, let's just write since m alpha is Eisenstein, we know p divides the constant coefficient of m alpha, but p squared does not. Now, if you remember from ages ago, we showed that the constant coefficient of the minimal polynomial was always given by the norm of your element. So since this constant coefficient is the norm k over q of alpha, we see that the norm from k over q of alpha has to be p times a, where p doesn't divide a, right? So it has to be divisible by p once, but not twice because it's Eisenstein. If you don't remember don't see where this norm is, why the constant coefficient is the norm, just go back to when we looked at minimal polynomials and norms and stuff. We had this result which told us that if you had a matrix and you look at characteristic polynomial and the second coefficient was a trace and the last one was a norm, and then we'd related this to the minimal polynomial. So therefore, we have, going back to this thing, we have this norm of this element of x to the d alpha to the n minus 1 over p. This is x to the d n p to the n minus 1 a to the n minus 1. I'm saying that the norm of alpha is PA, so if I take this element and replace it now by this, I get now this. Now this is divisible by just like this, which I can rewrite as x to the n alpha at a to the n minus 1 over p. But this can't be in z. In z, since p doesn't divide xd or a, right? A is not divisible by p by assumption. P, the norm is only divisible by p once. So once I've taken out the power of p, there's nothing left to divide a. And this gives us a contradiction. So this can't be in z since p can't divide xd or a, and this gives us a contradiction, since what's this, proposition 2.1.19 says that the norm of an algebraic integer always has to be an integer, and we just worked out. We said that this was an algebraic integer, and I just worked out its norm, and I've just realized that it's not an integer. It says the norm of an element of OK must always be an integer. Okay, so this is a long proof, but it's quite useful. This will be very useful. The result will be very useful for us for computing bases. So here's an example. How do we use this? Example 2.2.22. So let alpha be a root of let's go back to x to the 8 minus 2. Then by the previous time we looked at this example 2.2.20, we know that this matrix, this basis, 1 alpha to the 7 has discriminant 2 to the minus 31. So we only need to check. So when we said if we had an integral basis, so if we didn't have an integral basis, then we could find a smaller one where you take out some prime to the power, you take out some square prime of the discriminant. Let me say this again. If you started with a basis of algebraic integers and it wasn't an integral basis, then this lemma that we saw before, 2.2.7 or something, said that you can find a new one where the discriminant is smaller, and the difference is that you've now, the difference between discriminants is that now you've divided the old one by p squared, where p is some prime. So if I could prove that so for me to check that I need to have an integral basis, I need to now try and take out as many factors of square primes from my discriminant, and then eventually this will end, and I'll end up with an integral basis. So in this case, the discriminant is just some power of 2. So we only need to check at p equals 2. But m alpha satisfies Eisenstein with p equals 2. Therefore, lemma 2.2.21 tells us that this must be an integral basis. Since, so let me just combine the two and show you what. So this one says, if my polynomial was Eisenstein at 2, then none of these elements are algebraic integers. Right? None of the elements like this, with these xi's between 0 and p minus 1. None of these elements can be algebraic integers. And if we go back up to lemma 2.2.7, it said, if you didn't have an integral basis, then you could find a new one, and the new one would be given by taking an old element and replacing it by an algebraic integer of this form. So I'll never be able to find a new basis, because to find a new one I would have to replace something, but the thing that will replace it is an element which the other lemma has just told us that can't exist. And it can't be, the lemma 2.2.21 tells us that none of these elements are ever algebraic integers. So if you were to run through this new lemma with this algorithm for computing the integral basis, you'd be saying, okay, I need to now find an element like this to replace some basis element by, but none of that, you'll never be able to find that one by, because it doesn't exist, because your polynomial is Eisenstein. Great. So this is actually an integral basis. Cool, and we'll do lots of examples of this in the problem sheets and so on. But I'll leave it there for now, and then next time we'll look at some computing discriminants for some nice looking number fields, which will make calculations a lot easier later on. So I'll stop here.